Hello, my name is Wei-Chen Lin, and today I'm presenting my talk on an evaluation of MPI plus OpenMP on heterogeneous HPC systems. To motivate and give background to my topic, let's first discuss the current landscape of heterogeneous systems in HPC. Recent developments in HPC hardware have shown that modern HPC developments are highly heterogeneous. A quick survey of the top 10 HPC machines in the latest top 500 list shows that all but 3 HPC deployments have accelerator devices of some kind. This is usually AMD or NVIDIA GPUs. This paints a complex picture for programmers who wish to target these HPC machines. Their code would have to work well on different kinds of hardware with different and unique performance characteristics. For example, different CPU architectures have varying capabilities, and programmers porting their program across architectures will need to be aware of this to achieve a performant port. And in the top 10, we see at least 2 different kinds of CPU architectures, x86 and ARM. On GPUs, hardware vendors typically provide a first-party programming model that exposes all hardware capabilities as optimized for their own hardware. For example, CUDA for NVIDIA and HIP for AMD. However, the portability of applications that use these vendor-specific models is often limited to the hardware of the particular vendor. As HPC hardware is a fast-moving target, it is quite common for scientific software to outlive the hardware that it is originally targeting. And so, it becomes unproductive to rewrite or re-optimize code for new or different hardware platforms every few years. To address this, new parallel programming models have appeared, and existing ones adapted to act as an abstraction to shield programmers from aforementioned limitations. These programming models help programmers express parallelism through a coherent API that is designed to map closely to the underlying hardware. Models in this category include directive models such as OpenMP, which add support for heterogeneous device offload in newer revisions. In the same vein, models such as SYCL, COCOS, and Standard PAR fill the gap for targeting a seamless C++ experience. Modern heterogeneous shared memory parallel programming models are predominantly designed to encode parallelism on a single node. To scale to multiple nodes, HPC programmers would typically use a cross-node communication scheme such as MPI, together with the selected programming model, and this is known as the MPI+X paradigm. The success of an MPI+X implementation largely depends on how the node-level programming model, that is the X in the MPI+X, handles data placements and scheduling to accommodate for data access that is essentially foreign to the model. For example, many MPI vendors have support for directly accessing offload device memory using something that's called the GPU Direct RDMA. But to utilize this feature, the programming model are required to expose appropriate device level pointers. This presentation provides an overview of how the OpenMP model performs under single-node and multi-node scenarios on heterogeneous systems. We will first discuss how we can integrate OpenMP and MPI in heterogeneous scenarios. For comparison, we'll also briefly discuss how other programming models achieve the same integration. Then, we'll introduce how we evaluate these integrations. Here, we'll discuss our mini-apps and the test platform used. Finally, we present single-node and multi-node benchmarking results for our evaluation. We'll compare our MPI plus OpenMP results versus MPI plus X for SYCL, CUDA, COCOS, and the Standard PAR model. On CPUs, where there is only one address space, so integrating different programming models with MPI is straightforward. One simply needs to invoke the appropriate MPI calls with a pointer on the host. The MPI implementation is free to any optimization it sees fit to move data either within the node or to different nodes in the network. Here, the memory is resident on the host, so no extra data movement is involved. For GPUs, the story is more complicated. To reduce latency and copying, the optimal way to transfer data is to utilize the GPU's RDMA engine and use a device-aware MPI implementation. Device-aware MPI works in the same way normal host MPI calls work. But instead of calling with host pointers, the device pointer must be used. For this to be possible, the programming model must expose the underlying device pointer in some way. Note that native models such as CUDA and HIP gives you the flexibility to achieve this easily. We have two options to realize MPI plus OpenMP. First, we can simply copy the data from the device back to the host. Alternatively, to enable device-aware MPI, we can access the mapped memory's internal device pointer using the Use Device Pointer directive, introduced in OpenMP 4.5. Internally, the compiler replaced all references to the pointer declared in Use Device Pointer with the actual device pointer. Here, no additional synchronization is required. As by default, all regions are synchronous unless the node-way directive is present. Note that other models work mostly in the same way. You extract the underlying device pointer from the model and use those directly, as we will see in the next slides. First-party models like CUDA and HIP can also achieve the same thing using vendor APIs directly. Here, we can either do an explicit copy from the device to the host, as shown in option 1, or we can send the device pointer directly, shown in option 2. For C++ abstractions like Cocos, we have to break out some of the abstractions provided by Cocos. Here, the Cocos view holds the device pointer when compiled for CUDA. Once we have the device pointer, we can directly send the pointer using MPI. Like Cocos, much of the same thing can be done for SYCL. However, SYCL at the current stage have implementations that are not standard conforming yet. Different SYCL implementations have different integration strategies with the MPI, as shown in the code snippet here, where we have option 1, 2, and 2b. Standard PAR makes no distinction of pointers resident on different locations. Our only option is to opaquely send pointers with MPI calls. The underlying MPI implementation will be responsible for handling data movements in the most optimal way. To evaluate how different models integrate with MPI, we port the Cloverleaf and Teleaf mini-app with new MPI paths. We'll benchmark and analyze Cloverleaf and Teleaf ports of MPI+X on latest heterogeneous platforms, scaling from 1 to 8 nodes using MPI. We introduce results from multiple compilers where possible. In the next few slides, we'll introduce our mini-apps. The BLstream benchmark is an implementation of the McAlpin stream benchmark in a wide range of programming models. This benchmark is useful for helping us establish a baseline performance for scaling on a single node, as it currently does not support parallelism with MPI. Memory access pattern in BLstream, as shown here, are simple. The first 4 kernels are simple contiguous memory access that approximate the behavior of real-life memory bandwidth-bound workload. BLstream includes an additional dot product reduction kernel. This kind of kernel is frequently seen in HPC applications used for result correlation and convergence checking. To match results with past studies and to avoid unrealistic caching behaviors from newer platforms, we set the element size to 4 GB and leave the iteration count at default, which is 100 times. The benchmark records the highest attainable bandwidth from all iterations after the first. Cloverleaf is a 2D hydrodynamics mini-app that's part of the Standia's Mentivo benchmark suite and was recently adopted into the spec HPC benchmark suite. The application solves the compressible Euler equation in a structured 2D grid. The simulation holds multiple large double precision arrays implementing staggered fields. The mini-app exhibits both sensile and linear memory access patterns in a simulation loop. This benchmark has all the required ports to cover the programming models of interest discussed here. Cloverleaf uses a straightforward spatial domain decomposition with halo exchange for cross-node communication. Each MPI rank is responsible for its own chunk of the domain, and halo exchange occurs between ranks for each field after each step. Cloverleaf executes 4 asynchronous calls of MPI isend and MPI iReceive pairs to exchange halo regions with the 4 neighboring ranks. A blocking MPI wait all is then used for synchronous before advancing to the next time step. At the end of each time step, a set of MPI collectives, including MPI all-reduce and MPI all-gather, are used for computing delta T, profiling, and progress monitoring. As a mini-app, CLLEF supports input decks, which are predefined problem sets with results to validate against. We select 3 input decks for CLLEF: BM16, 64, and 256. Teleaf is a 2D diffusion mini-app that solves the linear heat conduction equation. Like CLLEF, this benchmark is developed by the UK MAC Consortium and is also part of Bentivo and Spec HPC benchmark suites. The core logic solves the system linear equations formed via sparse matrices. The mini-app accesses memory with the 5-point instance of the computer's sparse matrix vector product, as well as a simple linear access for initialization and MPI halo exchange related logic. All ports of the Teleaf share the same driver, which includes all MPI related logic. Domain decomposition is similar to that of CLLEF's. Each MPI rank holds the chunk of the structured grid fields, with halo exchange per iteration to maintain correctness. Teleaf makes use of MPI send and MPI receive pairs, along with collectives like MPI all reduced for time step calculation, profiling, and error reporting. We use Teleaf's integrated conjugate gradients, or CG solver, for our experiments. Similar to CLLEF, Teleaf also has support for input decks. We use the BM5 deck as a template to generate decks with sizes and memory requirements shown in the next few slides. For validation, we compare our output against the reference serial version of the benchmark. The hardware platform used for the benchmarks in this presentation are detailed in this slide. For CPU platforms, we scale from 1 to 8 nodes. For GPUs, the most common topology for hardware vendors is the 4 GPU per node configuration. As such, we treat each GPU as a single data point and scale to 8 MPI ranks using 2 GPU nodes. Here, Intel PVC, or Intel Ponte Vecchio, employs a unique 2-tile design, so we have configured the machine to treat each tile as an independent device. Results on 8 PVC devices refer to 8 tiles packaged as 4 physical accelerator cards. While the measurements on NVIDIA hardware are performed on a NVIDIA DGX system with 8 GPUs per node, we configure these systems to only use 4 GPUs per node with a topology equivalent to that of a NVIDIA HGX node with 4 GPUs to match the results for all other GPUs. For software, we show MPI and compiler versions on the right. We used CodePlay's binary plugins for one API to enable targeting AMD and NVIDIA GPUs using the ICPX compiler. For problem size on the left, we select a wide range of inputs to test for constant API overheads or behaviors when data cannot fit into the cache hierarchy. We start our discussion on single node performance as a baseline to gauge how well each programming model performs without any MPI components. Here, we show compiler performance on single node runs. One node per rank denotes one NPDAR, or one node per rank, denotes a run where the programming model itself handles the parallelism. It's equivalent of setting OMP num threads to 1. 1T over R, or 1 thread per rank, denotes a run where we limit the parallelism of programming model to a single thread and perform intra-node scaling using MPI. On Intel x86 nodes, we observe a consistent performance drop where scaling with 1 node per rank, we believe the additional thread coherency requirements for our shared memory models in the main source is the main source of overhead. However, OpenMP performed well across at least two compilers, even in the 1 node per rank scenario. On AMD Milan, the results are mostly similar. Here, the system has 8 NUMA nodes, and OpenMP still performed comparably to the 1 thread per rank in the 1 node per rank scenario. Graviton 3E showed good performance across the board, which is remarkable for a platform of this age. This is similar to results from our previous studies presented back in SC22. Note that Graviton 3E's memory topology is a lot simpler than our x86 systems, with just a single NUMA node. On the GPU side, OpenMP performed on par with other models in the Triad case. For the dot reduction, performance on the NVIDIA compiler appeared to lack optimization. We have provided this feedback back to NVIDIA. Turning now to strong scaling, we limit our results to show only the best performing compiler for each model, and we're interested mainly in each model's scalability. Smaller problem sizes for CLLEF highlight the associated runtime overhead for each model. Overall, on x86 CPU platforms, 1 thread per rank on the bottom row scales better than 1 node per rank on the top row for most models for CLLEF. The performance of OpenMP and other models are pretty much on par with each other here. On Graviton 3e, the scaling of CLLEF is essentially linear for all models. Again, this is pretty exceptional for a platform of this stage. MPI here uses Amazon's EF8 network, which scales proportionally to the node count. Although large-scale experiments will probably be needed to evaluate EF8 for production runs. For Teleaf on the CPU, the shaded area indicates superlinear scaling, regardless of whether it's 1 thread per rank or 1 node per rank. OpenMP managed to outperform all other models in this benchmark. This indicates that OpenMP may have a more optimal reduction implementation, as Teleaf is highly dependent on this feature. Here, 1 thread per rank at higher ranks begin to exhibit superlinear scaling as the problem size after domain decomposition starts to fit into the faster levels of memory hierarchy. Like our CLLEF results, the scaling of Teleaf is essentially linear on Graviton 3e for larger problem sizes. We are observing consistent overhead for our SYCL results across all CPU runs for both Teleaf and CLLEF. Intel's SYCL runtime on CPUs was not competitive. For adaptive CPP, we believe the runtime optimizes for task throughput instead of task latency, hence the higher overhead for smaller problem sizes. Device-aware MPI proved to be successful in improving performance across all GPU platforms, as shown in the second row of the charts. CLLEF here requires less frequent communication across nodes with a smaller halo region, so we see less significant improvements. On AMD platforms, center power and the USM variants of SYCL fail to complete within a reasonable amount of time at any problem size for both adaptive CPP and ICPX. It appears that the MI100 platform is not configured correctly with hardware-assisted page migration support. Without this, unified memory performance essentially degrades to a mode where memory allocations are mostly host resident. Because of this, we have omitted standard power and SYCL results spread for the MI100 platform. OpenMP targeted outperformed SYCL here, which is Intel's native model for PVC. This is a bit of a surprise here. PVC's software stack is still in development, so we expect performance gap between models, especially for USM models, to improve. On all GPUs, Teleaf's BM5 4K input does not scale well because the problem size is insufficiently large, so further decomposition simply leads to extra API overheads. Except for MI100, OpenMP targeted compare favorably to other models. This is an encouraging result for compiler vendors. On MI100, OpenMP results from the ALMP compiler suffered from a thread contention issue with MPitch. We observed slower than expected forward progress in the collective calls. This is most obvious on runs with more than 2 ranks, as shown in the chart on the right. The total runtime spent in compute kernels is otherwise similar to that of SYCL. Again, Teleaf results on PVC showed that OpenMP target performance is highly competitive and easily outperforms SYCL. Device-aware MPI provided a significant speedup even in this intranode configuration. Finally, our results show that the performance portability of hybrid MPI plus X applications is currently achieved only on certain platforms with very specific compilers. OpenMP showed good performance on both CPU and GPU systems using different code paths, with CPU performance slightly ahead of GPUs. In general, we find that overall performance is not primarily dictated by the specific spelling of parallelism for each programming model, but how well the underlying implementation optimizes for the hardware platform. Furthermore, we show that single-node performance is not always reflective of the performance on single nodes using the same programming model. In particular, As our study focuses on strong scaling where the problem sizes are reduced at high parallelization, we found that not all models were able to exploit the additional resources available. We'd like to thank AWS, NVIDIA, and Intel for providing access to their hardware platform. We've used Cambridge's DSD3 and Isambard supercomputer for many of our results. And that's it. Thank you very much.